cost to manufacture lead-acid batteries and gave a substantial increase in capacity compared with plant S battery. 20. Fjore's method is still in use at OD, with only incremental improvements to paste composition, curing, which is still done with steam. Butte is now a very tightly controlled process, and structure and composition of the grid to which the paste is applied. The grid developed by Fjord was of pure lead with connecting rods of lead at right angles. In contrast, present-day grids are structured for improved mechanical strength and improved current flow. In addition to different grid patterns, ideally, all points on the plate are equidistant from the power conductor. Modern-day processes also apply one or two thin fiberglass mats over the grid to distribute the weight more evenly. And while Fjord had used pure lead for his grids, within a year, 1881, these had been superseded by lead antimony, 8-12%, alloys to give the structures additional rigidity. However, high antimony grids have via hydrogen evolution, which also accelerates as the battery ages, and thus greater outgassing and higher maintenance costs. These issues were identified by U.B. Thomas and W.E. Herring at Bell Labs in the 1930s and eventually led to the development of lead-calcium grid alloys in 1935 for standby power batteries on the U.S. telephone network. Related research led to the development of lead-selenium grid alloys in Europe a few years later. Both lead-calcium and lead-selenium grid alloys still add antimony, albeit in much smaller quantities than the older high antimony grids. Lead-calcium grids have 4-6% antimony while lead-selenium grids have 1-2%. These metallurgical improvements give the grid more strength, which allows it to carry more weight, i.e. more active material, and so the plates can be thicker. Which in turn contributes to battery lifespan since there is more material available to shed before the battery becomes unusable. High antimony alloy grids are still used in batteries intended for frequent cycling, for example in motor starting applications where frequent expansion /contraction of the plates need to be compensated for but where outgassing is not significant since charge currents remain low. Since the 1950s, battery S designed for infrequent cycling applications, for example, standby power batteries, increasingly have lead-calcium and lead-selenium alloy grids since these have less hydrogen evolution and thus lower maintenance overhead. Lead-calcium alloy grids are cheaper to manufacture. The cells thus have lower upfront costs, and have a lower self-discharge rate, and lower watering requirements, but have slightly poorer conductivity, are mechanically weaker, and thus require more antimony to compensate, and are more strongly subject to corrosion, and thus a shorter lifespan, than cells with lead-selenium alloy grids. The open circuit effect is a dramatic loss of battery cycle life which was observed when calcium was substituted for antimony. It is also known as the antimony-free effect. 21. Modern approach. Modern-day paste contains carbon black, blank fikes, barium sulfate, and lignogulfonate. The blank fikes acts as a seed crystal for the lead-to-lead sulfate reaction. The blank fikes must be fully dispersed in the paste in order for it to be effective. The lignogulfonate prevents the negative plate from forming a solid mass during the discharge cycle, instead enabling the formation of long needle-like dendrites. The long crystals have more surface area and are easily converted back to the original state on charging. Carbon black counteracts effect of inhibiting formation caused by the lignogulfonates. Sulfonated naphthalene condensate dispersant is a more effective expander than lignogulfonate and speeds up formation. This dispersant improves the dispersion of barium sulfate in the paste, reduces hydroset time, produces a more breakage-resistant plate, reduces fine lead particles, and thereby improves handling and pasting characteristics. It extends battery life by increasing end-of-charge voltage. Sulfonated naphthalene requires about 1/3 to half the amount of lignosulfonate and is stable to higher temperatures. 22. Once dry, the plates are stacked with suitable separators and inserted in a cell container. The alternate platism constitute alternating positive and negative electrodes, and within the cell are later connected to one another, negative to negative, positive to positive, in parallel. The separators inhibit the plates from touching each other, which would otherwise constitute a short circuit. In flooded and gel cells, these separators are insulating rails or studs, formerly of glass or ceramic, and now of plastic. In AGM cells, the separator is the glass mat itself, and the rack of plates with separators are squeezed together before insertion into the cell. Once in the cell, the glass mats expand slightly, effectively locking the plates in place. In multi-cell batteries, the cells are then connected to one another in series, either through connectors through the cell walls, or by a bridge over the cell walls. All intracell and intercell connections are of the same lead alloy as that used in the grids. This is necessary to prevent galvanic corrosion. Deep cycle batteries have a different geometry for their positive electrodes. The positive electrode is not a flat plate but a row of lead oxide cylinders or tubes strung side by side, so their geometry is called tubular or cylindrical. The advantage of this is an increased surface area in contact with the electrolyte, with higher discharge and charge currents than a flat plate cell of the same volume and depth of charge. Tubular electrode cells have a higher power density than flat plate cells. This makes tubular forward/cylindrical geometry plates especially suitable for high current applications with weight or space limitations, such as for forklifts or for starting marine diesel engines. However, because tubes forward/cylinders have less active material in the same volume, they also have a lower energy density than flat plate cells. And less active material at the electrode also means they have less material available to shed before the cell becomes unusable. Tubular forward/cylindrical electrodes are also more complicated to manufacture uniformly, which tends to make them more expensive. Than flat plate cells. These trade-offs limit the range of applications in which tubular forward/cylindrical batteries are meaningful to situations where there is insufficient space to install higher capacity, and thus larger, flat plate units. About 60% of the weight of an automotive-type lead-acid battery rated around 60 times H is lead or internal parts made of lead. The balance is electrolyte, separators, and the case. 8. For example, there are approximately 8.7 kilograms, 19 pound, of lead in a typical 14.5 kilogram, 32 pound, battery. Separators. Separators between the positive and negative plates prevent short circuit through physical contact, mostly through dendrites, treeing, but also through shedding of the active material. Separators allow the flow of ions between the plates of an electrochemical cell to form a closed circuit. Wood, rubber, glass fiber mat cellulose, and PVC or polyethylene plastic have been used to make separators. Wood was the original choice, but it deteriorates in the acid electrolyte. An effective separator must possess a number of mechanical properties, such as permeability, porosity, pore size distribution, specific surface area, mechanical design and strength, electrical resistance, ionic conductivity, and chemical compatibility with the electrolyte. In service, the separator must have good assistance to acid and oxidation. The area of the separator must be a little larger than the area of the plates to prevent material shorting between the plates. The separators must remain stable over the battery's operating temperature range. Absorbent glass mat, AGM. In the absorbent glass mat, AGM, design, the separators between the plates are replaced by a glass fiber mat so act in electrolyte. There is only enough electrolyte in the mat to keep it wet, and if the battery is punctured, the electrolyte will not flow out of the mats. Principally, the purpose of replacing liquid electrolyte in a flooded battery with a semi-saturated fiberglass mat is to substantially increase the gas transport through the separator. Hydrogen or oxygen gas produced during overcharge or charge, if the charge current is excessive, is able to freely pass through the glass mat and reduce or oxidize the opposing plate respectively. In a flooded cell, the bubbles of gas float to the top of the battery and are lost to the atmosphere. This mechanism for the gas produced to recombine, and the additional benefit of a semi-saturated cell providing no substantial leakage of electrolyte upon physical puncture of the battery, allows the battery to be completely sealed, which makes them useful in portable devices and similar roles. Additionally, the battery can be installed in any orientation, though if it is installed upside down, then acid may be blown out through the overpressure vent. To reduce the water loss rate, calcium is alloyed with the plates. However, gas buildup remains a problem when the battery is deeply or rapidly charged or discharged. To prevent overpressurization of the battery casing, AGM batteries include a one-way blow-off valve, and are often known as valve-regulated lead acid, or VRLA, designs. Another advantage to the AGM design is that the electrolyte becomes the separator material, and mechanically strong. This allows the plate stack to be compressed together in the battery shell, slightly increasing energy density compared to liquid or gel versions. AGM batteries often show a characteristic bulging in their shells when built in common rectangular shapes, due to the expansion of the positive air plates. The mat also prevents the vertical motion of the electrolyte within the battery. When a normal wet cell is stored in a discharged state, the heavier acid molecules tend to settle to the bottom of the battery, causing the electrolyte to stratify. When the battery is then used, the majority of the current flows only in this area, and the bottom of the plates tends to wear out rapidly. This is one of the reasons a conventional car battery can be ruined by leaving it stored for a long period and then used and recharged. The mat significantly prevents this stratification, eliminating the need to periodically shake the batteries, boil them, or run an equalization charge through them to mix the electrolyte. Stratification also causes the upper layers of the battery to become almost completely water, which can freeze in cold weather. AGMs are significantly less susceptible to damage due to low temperature use. While AGM cells do not permit watering, typically it is impossible to add water without drilling a hole in the battery. The recombination process is fundamentally limited by the usual chemical processes. Hydrogen gas will even diffuse right through the plastic case itself. Some have found that it is profitable to add water to an AGM battery, but this must be done slowly to allow for the water to mix via diffusion throughout the battery. When a lead acid battery loses water, its acid concentration increases, increasing the corrosion rate of the plates significantly. AGM cells already have a high acid content in an attempt to lower the water loss rate and increase standby voltage, and this brings about shorter life compared to a lead antimony flooded battery. If the open circuit voltage of AGM cells is significantly higher than 2.093 volts or 12.56 V for a 12V battery, then it has a higher acid content than a flooded cell, While this is normal for an AGM battery, it is not desirable for long-life. AGM cells that are intentionally or accidentally overcharged will show a higher open circuit voltage according to the water lost, and acid concentration increased. 1 amp-hour of overcharge will electrolyze 0.335 grams of water per cell, some of this liberate antimony flooded battery. If the open circuit voltage of AGM cells is significantly higher than 2.093 volts,